All right, so we're in 9.2, part 2. All right, let's get started, guys. So I said yesterday that we would talk quickly about why the sum of a geometric series works out the way it does. So I want to go through that quickly. It's a very, very quick demonstration, and I remember this I learned this in my pre-calc class in high school, so I remember this from when I was in high school. So for a geometric series, we have the sum n equals 0 to infinity of a r to the n. So I'm going to write out the nth partial sum. S sub n equals a plus ar squared plus dot 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 ar to the n. So there's my nth partial sum. Now here's a tricky part, kind of the crux of the whole thing. I'm going to write as sub n is a squared plus, I want to do rs sub n. Maybe I didn't remember from high school. Rs sub n, I get ar plus ar squared plus ar to the third plus dot 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 ar to the n plus 1. Now I'm going to take the difference, s sub n minus rs sub n. Well, everything, when I subtract, this cancels, this cancels, this cancels, everything cancels but this term and this term. So I get a minus ar to the n plus 1. I'm going to factor the s sub n and divide. So I get s sub n equals a minus ar to the n plus 1 over 1 minus r. Factor out the a in the numerator. If the absolute value of r is less than 1, as n approaches infinity, what is r to the n plus 1? What's the limit of that? If the absolute value of r is less than 1. 0. So as n approaches infinity, my sum, nth partial sum, is a over 1 minus r. So that's why that sum formula works out. And that's kind of a slick little proof. All right. So one of my favorite problems having to do with series. Any questions there? Okay. So let's look at this problem. We want to, well, first off, I'm not even going to say the problem. Let me just write this number down. 5.23. Repeating. What do we know about that number? It repeats. It's rational. A rational number is a repeating decimal. So it's a rational number. So how can it be represented? It's a rational number. We can represent it as a fraction. Forgot my F. And what kind of fraction? Right? Rational number is a fraction of and or their. Could a rational number be negative? Could be. So fraction of integers. I want to write 5.23 repeating as a ratio of integers. Any idea how we're going to do this? What do you think, Max? It has to do with what? Series. It does have to do with series. So I'm going to rewrite this as 5 plus 0.23 repeating. So I'm pulling that 5 out. Well, let's write, I'm going to rewrite 0.23 repeating kind of like we did back in elementary school, where we said it's this many times the hundreds, this many times the thousands. So this equals 5 plus 0.23 plus 0.0023 plus 0.00023 plus dot dot dot. So that gets my repeating part. Now I'm going to write this as 5 plus 23 over 100 plus 23 over, how can I write 10,000? How about a power of 100? 100 squared plus 23 over 100 cubed. I'm going to rewrite this again. 5 plus, I'm going to factor out a 23 over 100. 1 plus 1 over 100 plus 1 over 100 squared plus dot dot dot. And I can rewrite this now as 5 plus 23 over 100 times the sum, n equals 0 to infinity of 1 over 100 to the n. And I know how to find the sum of this, right? We just talked about how we did it. We talked about how we did it yesterday. So this is 5 plus 23 over 100 times 1 over 1 minus 1 100, which is 5 plus 23 99ths. And if I write this as an improper fraction, 5/1899. And now we've written this repeating decimal as a ratio of integers using geometric series. Isn't that a nice thing? Now we can. That may be some kind of algorithm like this. Are we going to check, Seth?
Yeah.
Okay, let's check with your calculator. Make sure we did this right. All right, so questions on that? All right, we know how to turn any repeating decimal into a fraction of integers. I think that's a really fun thing. Okay. All right, just a couple more things today. I want to note something that we're going to use throughout the unit on sequences and series, and this comes up fairly often. That when we're talking about convergence isn't affected by deleting a finite number of terms from the beginning of a convergent series. So we can delete a finite number of terms from the beginning of a convergent series, and it doesn't alter the convergence. So, for example, we have the sum n equals 4 to infinity of 1/2 to the n. So this is a geometric series with the first 4 terms removed. Well, both of these converge. So removing a finite number of terms from this series doesn't affect the convergence. It does affect the sum, though. And to find the sum of this first one, how would I find the sum of this first one? Well, we know how to find the sum of the second one, right? So we find the sum of this geometric series, which we have a formula for, a over 1 minus r, and then we just manually sum 4 terms and subtract those first 4 terms from this sum. So deleting a finite number of terms from a convergence series doesn't affect the convergence, it does affect the sum. So we can find the sum of that finite number of terms, hopefully, and we could subtract it from the sum of the original series if we can find it, and find the sum of the series we're interested in. So that's an important thing to remember, is that deleting that finite number of terms doesn't affect the convergence. Yes?
Do you still have to do it manually if the number's really big, like any was 10,000? Like, would you still have to find this 10,000?
Well, we could, for a geometric series, let me go back here. Here's a partial sum. There's a partial sum for a geometric series. So there's a formula for a partial sum. So we could use that if it's a geometric series. And geometric series and now telescoping series are the only 2 kinds of series that we know how to find the sum of. So the main thing, normally you're not going to be asked to find the sum. It's just going to be important to know that deleting a finite number of terms doesn't affect the convergence of the series. That comes up not frequently, but it's a fact that you need to remember. I just want to again mention the properties of infinite series. We can form the sum of the limits if we want. If we have 2 infinite series and we want to add them together, we can add their limits together. We can add, subtract the limits. We can multiply the limits by a constant. So I'm not going to write out all those properties, but we can add and subtract limits. For adding and subtracting series, we can add and subtract limits, and we can also multiply a limit by the constant. So if we multiplied this convergent sequence by a constant to find the new sum, we would just multiply the limit by a constant. So I'm not going to write all those out, but we can do some arithmetic with limits. All right. The next one of the big tools, one of the important things is the nth term test, or the limit of the nth term. And this is a tricky idea in series. So we want to look at the limit of the nth term. So we're going to state a theorem here. If our series converges, then the limit as n approaches 0 of a sub n equals 0. If the series converges, the nth term, the limit as n approaches infinity of the nth term is 0. The converse of this theorem is not true. That's an important thing to remember. What would be the converse of this theorem? How do we make the converse of a theorem? Right, we just turn it around. So that we cannot say if the nth term approaches 0, then the series converges. We cannot say that. So that is not true. But the contrapositive, talking in logic terms now, contrapositive is true. So the contrapositive is if we turn it around and we put a not in front of everything. If the limit as n approaches infinity, a sub n not equal to 0, then our series diverges. So our contrapositive is true. Contrapositive is logically equivalent to the theorem itself. So our converse is not true. We can't say that if our nth term approaches 0, then our series converges. As much as we would love to say that, we can't say that. But we can say if our nth term does not approach 0, then our series does not converge.
Is that the limit approaching infinity or 0?
This should be infinity. N approaches. Sorry. N starts at 1. So we only go in the positive direction here. I just forgot the other half of my infinity there. So if our series converges, the nth term approaches 0. If the nth term does not approach 0, then our series does not converge. But we can't say that our series converges because the nth term approaches 0. And the proof of this is very easy. If this series converges, I should have a converges in here. If this converges. If the series converges, then the partial sum has to converge to a limit. So if we can't add anything to the partial sum. If we add something to partial sum, then our series isn't converging to our limit. So that's the gist of the proof there. Is that this has to have a limit, so we can't add anything extra to it. So what's our most famous example here of a series? We should all know this one. A series where the nth term approaches 0, but it diverges. What's our most famous example? Do we remember? A harmonic series. The harmonic series diverges. And that's not factorial, that's an exclamation point. Where a harmonic series diverges. Harmonic series, the sum, n equals 1 to infinity of 1 over n. Harmonic series diverges. The nth term approaches 0 as n approaches infinity, but this series diverges. So let's look at the harmonic series really quickly. N equals 1 to infinity of 1 over n equals 1 plus 1/2 plus 1/3 plus 1/4. I'm going to move this down so I have a little more room. Equals I'm just going to write out a bunch of terms. So the way we can show this directly, if I add these two up, those two are greater than 1/2. If I add those 4 up, those 4 are greater than 1/2. If I add the next 8 up, they're greater than 1/2. So the harmonic series is greater than 1 plus 1/2 plus 1/2 plus 1/2, which diverges. So the harmonic series is the most the most famous, the most common example of a series whose nth term approaches 0, but the series diverges? Yes? Alternating harmonic series. Do we remember about an alternating harmonic series? Alternating harmonic series converges. So it's a strange thing. And we'll talk about another strange thing that happens with convergent alternating series. Turns out that you can rearrange the terms of a of a divergent alternating series to get any sum you want. So we can't rearrange the terms of an alternating series. We'll talk about that later. So harmonic series is the most famous example, or the most common example of a series whose nth term approaches 0, but the series diverges. And we will do a lot of comparisons with the harmonic series. So it's an important one to remember. So as much as we wish that if this nth term approaches 0, that our series converges, not necessarily the case. All right, questions today? So the main things from today: repeating decimal, we know how to turn that into a ratio of integers, and we talked about our nth term test. That if our nth term does not approach 0, then our series does not converge. All right. Homework.